with this bell work, we are trying to figure out why one person would reject the null and the other person would fail to reject the null. Well, we can see from the beginning it's going to be a two-tailed test versus a one-tailed test. So what this is saying, if they're using the same significance level, they must have gotten a p-value that fell between 0.05 and 0.025. All right, and the reason for that is that with the one-tailed test, as soon as you calculate the p-value, you're done. And so it would have fallen in this range and you would have rejected the null. Now the other person would have gotten the p-value in this range and then doubled it. So if you double it, now the p-value is going to fall somewhere between 0.05 and 0.10. Now in this range, this is the range where we would fail to reject the null hypothesis. So that is where we're at. Okay, so if that makes sense, we know the range has to be between these two numbers. And so now we want to figure out which of these z-scores give us a p-value between the range. And it turns out that negative 1.8 and 1.8, they're the same thing, right? You're going to get the same z-score. So now we need to figure out, should it be a negative or a positive? And since our one-tail hypothesis was this one, what we're saying is that our p-value should be that our true outcome or the sample outcome from here would have been way down here somewhere. And that means that the area to the left of that test statistic right here, our z-test statistic, would have been, I think it's 0.035 or something. It's in that range. Now, this proportion, this test statistic is showing that we're going to get a true proportion that's far less than 0.85. So we want, maybe that's a convoluted way of saying we want the negative z-score in this case, not the positive one. Does that make sense? Okay. So hopefully it does. I'll try and clarify that more if you have more questions on it later. So we are learning a new chi-square test called the chi-square test for homogeneity. The good thing about this is we're going to have to learn a different way of doing a chi-square test for this. The good part about this is that once you learn the chi-square test for homogeneity, the next one, which we call the chi-square test for independence, is basically exactly the same thing. And it's actually, the hardest part about these is figuring out when you should use one versus the other. But mathematically, they're pretty much, in fact, I'm trying to think, mathematically, they're identical. So that's good. You're kind of getting two for the price of one today. So here we go. The chi-square test for homogeneity is used to determine if the distributions between two samples on the same variable are the same. So let's kind of do a bit of an analogy here. When we did a one sample z-test, we were comparing a single sample that was taken to an assumed value. So 70% of people, according to this national statistic, have this characteristic. You do a sample, you compare your proportion to that claimed value. So that's what the one sample was. And that was similar to the chi-square test for goodness of fit, because you're already given a distribution and you're comparing one sample to that distribution. So if you're following this analogy, hopefully that's clear enough. The chi-square test for homogeneity is similar to a two sample z-test. We don't have kind of a baseline that we're comparing it against. We're just taking two different samples. We're saying, is this sample and this sample, are they essentially the same thing, or is there a difference between them? So you can see right here, we have two samples and we're seeing if they are, oh no, I put the wrong there. If they're similar, oh, I'm fixing it, sorry. Oh, whew. That was a close one, guys. Get back to it. And we're seeing if they're similar to each other, regardless of any claimed distribution. All right. So again, by way of analogy, we're kind of seeing what the chi-square test for homogeneity is all about. This is your definition from the textbook. It provides just a little bit of you know, what scope for what this test is all about, if you want to think of it that way. I'm not planning on reading it, but maybe right here, it finds expected counts based on the overall frequencies adjusted for the totals in each group, under the assumption that the distributions are the same for each group. Now that actually reading it doesn't help a whole lot. So let's just jump into it. So maybe that was a waste of time. So here's, I will say this, in your, I can't remember if I fixed this. I think I did, but I fixed it with this right here. There is, in your reference posters that are in the Canvas for this unit, it has this slide that shows your one sample and variable one. Anyways, you can find out which chi-square test you want to use. The thing is, there was a mistake. If you have two samples with compared to one variable, that's a chi-square test for homogeneity. That's what we're doing today. Tomorrow we're going to do one sample, two variables to test for independence. Okay, so I just wanted you to be aware of that. And now we're going to look at this, and you can see the difference. It's actually pretty easy to tell if it's got to be a chi-square test for goodness of fit or for one of the other two. So that's kind of where the fault line is in chi-square tests. You're either going to have your chi-square goodness of fit, or you're going to have chi-square homogeneity. And the hard part is determining if it's supposed to be homogeneity or independence. But telling these two apart, you know, whether it's that one or one of these two, that's easy because these are always going to have a two-way table. So that's going to be your telltale sign. All right. So the null and alternative hypotheses here is that well, how do we phrase it? There it is. So I forgot exactly how to phrase it. No difference in distributions, or that there is a difference in distributions. So again, there are different ways I could have phrased that. I just wanted to kind of have a consistent one. Our null hypothesis is that, and I'll kind of jump into, I just want to go ahead and lay out the hypotheses to begin with. There is no difference in the distributions. And the alternative hypothesis is that there is a difference in the distributions. So what does this mean? Now, maybe I should have started with this, but I think it's just as fine that we start with the hypotheses and come back to it. So for a class project, Abby and Mia wanted to know if the gender of an interviewer could affect the responses to a survey question. The subjects in their experiment were 100 males from their school. Half of the males were randomly assigned to be asked, would you vote for a female president, by a female interviewer? The other half of the males were asked the same question by a male interviewer. The table shows the results. It was some tricky sort of sociological experiment going on. Okay, so what we have is the gender of the interviewer and then the response to the question. So what we're looking for in this homogeneity test is this distribution the same as this distribution? And our null hypothesis is that there is no difference in the distribution. Now, obviously, we're getting different numbers. We're not saying it's going to be exactly the same count, but is this difference enough, just like with the goodness of fit, is this difference enough for us to determine that there's a difference and maybe the gender of the interviewer will affect responses? Does that make sense? So we're good with this so far. All right, so now we have a two-way table that's summarizing all of our data. And again, this is one of your reference slides. You can have these available at any point when you're going through this. You just can't have them when you're taking the AP test. So anyways, our hypotheses are pretty much always going to be the same. If we have two different distributions about the same variable, then there's no difference in the distributions. Alternative is that there is a difference. Let's move forward. Show the calculation for the expected counts in the male yes cell, whatever. Then provide a complete table of expected counts. This is the one where it gets a little more challenging. All right. It's really not that bad, but let's kind of look at this, and we're trying to find the expected counts. And what I'm not actually going to have the row totals and the marginal totals. So this only represents this part of the table. And I want to find expected counts. So what I want to do to find expected counts is I want to take, for this cell right here, which is the top left, I want to take the row total, 69, times the column total, which is 50, multiply those together. So that's going to be 69 times 50. And then I want to divide that entire thing by the total amount, by the bottom right cell. And I'm divide that by 100. And so we can do that real quick. And that should be 34.5. So now whenever I want to find the next one, I'm going to move to the right. So now I want to find the expected value of this is going to be the row total times the column total divided by the total count. And so, I mean, in this case, it happens to be the same thing because the row total is 69 and 50. We got it 34.5. Now this one doesn't look as exciting because there's actually a 50-50 split right down here at the bottom. So whatever we get on the left is going to be on the same on the right. But when we get to our next example later in class, we're going to see that we don't end up with the same values left and right. So we really only have to do this calculation one time. Okay. So let me now find what this expected value will be for that part, that cell. So it's going to be 11 times 50 divided by 100. And the expected count here is going to be 5.5, which will be the same. And then lastly, we can look. Now, again, if these were not the same value down here, I couldn't just copy it over. I'd have to calculate each cell individually. So let me know if you need me to stop or slow down if anything isn't making sense. But now I can do the last one. That's going to be 20 times 50, and then divide that by 100, which is going to give me 10 and 10. All right. So it's a little bit more convoluted how we find our, what am I talking about? It is a little bit more convoluted how we find our expected values, but luckily it's the same for both this and the independence, the test for independence tomorrow. And you can see that right here. Row total times column total divided by table total. Okay. So we've got those values. We're going to calculate the chi-square test statistic. Are we going to do this by hand? Yeah, let's do this by hand. And then we'll find out how we do this in the calculator, which is a little less straightforward than the other one was. So yes, male was 30. And then we have our expected counts right here. You guys can go ahead. I'll plug in the expected counts just because they're right there. You guys can plug in the observed counts while I'm doing this. All right, so we got this table filled in, and to cap off our chi-square test, what we need to do is take all these different contributions and add them together. And remember, the higher the number is, the more it varies from what we expect or from these two being homogeneous. And therefore, we would reject it if it's a really high chi-square. We'll find out if this is high enough to reject in just a second. So we're not going to take too long on this because, again, we will let the calculator calculate this for us. But 4.694 is what I got. So that is correct. Let's go ahead and find out, is this a high enough chi-square value in order for this to be rejected? The difficulty is, well, wait. Oh, so the difficulty, and I'm just going to maybe run through this. I forget where it is in my presentation. We'll do the matrix stuff in a second. The degrees of freedom. Okay. Where do I do that? That should have been right here, but somehow, there it is. Your degrees of freedom for a test for homogeneity is going to be calculated a little differently. So for goodness of fit, we took the number of categories and we subtracted 1. Now in the test for independence and homogeneity, what we do is you take the number of rows minus 1 and multiply it by the number of columns minus 1. Essentially, this is the same thing. So let me come back to this right here. So in this case, we're only worried about this part right here, the conditional distribution of everything, not the marginal totals. So I've got 2 columns and I've got 3 rows. And so I'm just going to take the 2 minus 1 and 3 minus 1, which gives me 2 times 1. So I'm going to have 2 degrees of freedom for this. Now this follows, it's almost like we're scaling this up. So if I had a goodness of fit test, I might have all these, 4 different categories. And I say my degrees of freedom is just going to be these 3. And I ignore the last category, right? So now if it's 2-dimensional, I've got another category or another variable, or maybe in this case, 2 different distributions that I'm considering. I want to do all of these values as well. I want to have those categories considered, but then I also want to have 1 less as far as my amount of rows go. So it's this like number of categories in rows, number of categories in columns. And then I multiply that together to give me the total degrees of freedom. And I hope that wasn't a convoluted way of explaining that. But essentially that's what we have here. We have 2 degrees of freedom for this particular example. So if I go to my chi-square test, I already have a chi-square value of 4.694. 2 degrees of freedom, 4.694. Where's the chi-square value going to fall between, or where's the p-value going to fall between? Erase this.
Wait, could you say one more time what you multiplied to get the degrees of freedom?
Yeah, I did the number of columns minus 1 times the number of rows minus 1. You can see right here where I did my calculation. So 2 columns and 3 rows. So what is the p-value going to be between? So because our chi-square is 4.694 and we're looking at the second row for 2 degrees of freedom, it is going to fall somewhere between 0.1 and 0.05. And we will be able to calculate this, and we can maybe do that in just a second. But there is what we can determine. And assuming we started with a 0.05 significance level, then at this point we could say we would fail to reject the null hypothesis. And I'll pause right there to see if there are any questions on this. And when I ask if there are any questions, maybe it's something you're like, maybe I just want to see another example, and you can ask to go through another example later. We are going to do another one before class ends, but let me go ahead and clear this table. Okay, now here's how we can do this on the calculator. Because the 2 distributions are found in 2-way tables, we'll need to set up matrices. And hopefully you learned how to do matrices in your calculator, maybe in Algebra 2 or in another math class. And there is a way of doing this, you're going to have to hit second, and then it's your inverse function button, the x to the -1. So if you hit second and that, it's going to bring up your matrix menu. And what you want to do is you want to go over to the right where you can edit matrices. And you want to put your observed counts in matrix A, and you want to put your conditional, you want to put the, don't include the marginal distribution. And in matrix B, you want to put the expected counts to be calculated. And it's always going to be rows by columns as far as the size of your matrix goes. So these are going to be, and maybe I'll go back a slide, but it's going to be a 3x2 matrix. And I know you don't have those numbers. So let me, okay, we'll not worry about doing the actual chi-square test yet. Let's just plug these numbers into two matrices.
Wait, I got lost trying to find the buttons. You go second matrix. And then
Yeah, second matrix, and then you go over to the right when you're in there to edit.
Okay.
And you want to go ahead and leave it for matrix A, do the observed counts. And matrix B will be the expected counts.
Okay.
But you're actually going to create some matrices on your calculator. And so these are not the correct numbers plugged in. This is what I did the last time I created matrices last semester. But it's a 3x2 matrix, and you can see if it's going to look the same. And then you can go ahead and go down, and for every single cell in your matrix, you can go ahead and plug in the right numbers. So I'll actually do that now and then show you what mine looks like when I'm done, which now I am. So you can see I just took the same data and plugged it in. And then you'll want to go back, and I haven't found a faster way of doing it than just exiting from this and going back into the matrix menu. But then for B, you can plug in all the expected counts. So I just wanted to show this is now matrix B set up with my expected counts, and it looks like the same thing that you see on the screen there. I'll give another little bit of time, make sure everyone has gotten that far. So now that we have our two matrices set up, and I tell you to go ahead and leave the observed counts in A and the expected counts in B, because when we go ahead and do the chi-square test, it's already set up that way. So what we need to do is, like always when we're trying to access a test, you go to Stat, Tests on the far right, and if you go all the way down to option C, you're going to find your chi-square test. And you've already done the hard part of this. So again, Stat, Tests on the far right, option C is your chi-square test. And notice it already has preloaded in there when you select it that your observed counts are in matrix A, your expected counts are in matrix B, and all you have to do is calculate. And there we go. 4.246, 4.247, and then the p-value is 0.1196. So somehow we got a little bit off in our calculations. I don't know what we did wrong, but whatever the case, because we got 4.694. But regardless, I mean, we're still in the same ballpark, so it's not like we totally botched it. Something happened. So knowing that, our p-value, we thought it was supposed to be between 0.05 and 0.10. It's actually 0.1196. So that error that we made actually made our p-value a little bit higher than we expected. But still, the calculator runs through, or did you guys get this number? Did you get the 4.24?
Yeah.
Okay, I just, because I was sitting there like, wait a second, maybe I put numbers in the calculator wrong. But no, if we're all getting the same thing, then yeah, you can see what's going on. So the chi-square test, we will run that through the calculator, especially if you have imagine you have a huge matrix. That would be a lot of calculations to do. This is a fairly small one. So there you go. This presentation, if you need to remember how to do it, actually have, I'm going to load in some reference pages for all of your calculator functions that we've been learning. So that's something that you might want to have access to. And I will upload that today, and it'll probably be under your references at the top of your modules, but I will point it out to you tomorrow just in case. Okay, so now you can see what your chi-square curves look like. And these are highly variable. You'll notice that it starts off with your degree of freedom 1 and 2, like they are this weird almost power curve looking sort of thing going on. And then with 3, you get a little bit of a normal, skewed normal distribution. And by the time you get up to 10 degrees of freedom, it's starting to look more normal. So you can see, of course, as degree of freedom increase, the skew decreases. So it's just good to know, as far as this goes, it's good to know what these curves look like. And we're always doing kind of a right-tailed test for this. Is the value that we got, that value or more extreme to the right, likely or not? Okay, so I don't know what's going on here. We kind of already finished this. We do have the same conditions for inference in that it has to be random, and the independent means that the sample size is less than 1/10 of the population. Now, another kind of caveat to this is if you are sampling without replacement. And if the events themselves are independent, then that's fine. We don't even need to worry about 10%. We can just say the events are independent. So we had that example yesterday where someone created a die and was rolling it. Well, because each die roll is independent, we can actually ignore the 10% condition. We can say the die rolls are independent, therefore we don't need to meet the 10% condition. Large counts is the same as it was for the goodness of fit. All expected counts had to be at least 5, and we had that in ours because the smallest one was 5.5. Okay, now we're going to go through just another example, and that'll be basically it for today. You can just get some more practice with this on your own. A survey of articles from the New England Journal of Medicine classified them according to the principal statistics method used. The articles recorded were all non-editorial articles appearing during the indicated years. Let's look at whether these articles use statistics at all. And now there's the question, has there been a change in the use of statistics? And this is a test of homogeneity because we're saying with these, and it can be more than 2 samples, with these 3 different samples that were taken on one variable, did they use stats or did they not? So of these 3 different samples, does it appear that these distributions are different, or are these distributions the same? So let's create some hypotheses. Well, first of all, we can go with the significance level. What should our significance level be? 0.05. Why not? The null here, does anyone remember what our null is for this test? There is no difference in the distributions. So our starting point is that the use of statistics has not changed through time, essentially is what we're saying. There is no difference in distributions. And then of course the alternate would be there is. And notice that we are not concerned with how the difference has occurred. Or is there more use of statistics or not, or less? But we can look at the actual numbers and determine if there is a statistically significant difference. Then we can do a further analysis to say it looks like statistical use is going up over time, or it's going down over time. So let's now move forward and let's name this procedure. So I'm going to erase this. The name of this procedure is a chi-square test for homogeneity. And again, this is when you take 2 or more samples and you want to see if there's been a difference in distribution in one variable over time. And we want to check conditions. All right, our conditions: random, 10%, and large counts. Large counts. So is this random? Yeah, this one might be a little bit tricky. It doesn't say it's random. And what a survey of articles, does that mean in this case that they looked at every article?
Yeah, it's hard. I don't know if they're saying like they selected articles, if they chose them or like if they just, yeah, I don't know.
So what we can do is we can add caveats to this. We can say, you know, maybe this was not, maybe we haven't met these conditions. So in checking these conditions, is it random? Yeah, we can just say what we think. It's at least showing our statistical knowledge, because we can say the survey, it might be random. It might be a random survey, or it might include all, be a census essentially. So I'm kind of mixing, when I created this question, I didn't actually write the question, but I took a question from the book and I mixed it with this process. Now, typically it's not going to be so ambiguous as far as what our answer is going to be, but we do need to be prepared to kind of look for these things. So, therefore, you can put an asterisk next to this one, like it might not be random. 10%. Well, if it's all of the articles, then this is a census and it's no longer a sample, right? We're getting everything from the population. But, we will assume that this is less than 10%, less than 10% of the population. And then right here in parentheses, but it might be the entire population. That's a big jump, isn't it?
How do we check the conditions if we just like say we can assume
Well, in reality, if we didn't meet these conditions, we wouldn't do the test. But in the AP Stats class, if we don't meet the condition, we say, well, this might not be a correct outcome based on not meeting the conditions, but let me show you that I know how to do it, assuming it is correct. Now, again, a lot of times on the AP test, they'll even say, assume the conditions for inference have been met. And you don't even need to check the conditions. Now, but that is a good question, because in reality, we would look at this and we'd say, oh, we haven't even met the conditions, so I'm not going to do that test. All right, and large counts right here. We need to find our expected counts. I'm going to kind of shove this in the corner. So I need to figure out how many would I expect from all of these. So this is where, notice we don't have a nice 50-50 breakdown in either one of our variables shown here. And technically these aren't variables. There's one variable that's tested over 3 different samples. All right, if you're with me on that, I basically circled everything on that table, didn't I? So what I want to do for the first cell, I want to take the row total times the column total divided by the table total. All right. And then if I go all the way through, it's going to be for every single cell, that row total times column total divided by the table total. I'm going to see if you guys can come up with what the expected counts for this table should be. So we finally got that table filled in, and large counts, remember, we just have to make sure all of our expected counts are at least 5. This condition at least is pretty straightforward to check, and yes, we met this. 21.9 is the smallest, and that's greater than 5, so we're good. Okay, I will not erase this table because we're going to need it for the next little bit. Let's see if I can erase this pretty quickly. All right, and I'll clear the table off a bit. So conditions were a little bit weird on this one, but now we can go through and we can do the work. Now, let's talk about how we fill this in. We did this the other day, yesterday, in fact, but it changes a little bit. Our specific formula stays the same. It's the chi-square test, and that's always found. So that's the sum of your observed minus the expected squared all over the expected. And we want to show what that looks like. So we're going to have the observed 90 minus the expected 63.1 squared divided by the expected, which is 63.1. So I want to go ahead and show that. 90 minus 63.1 divided by 63.1. Sorry, and that should be squared. Plus, and then we have another one. But I don't have to show that one. I'm going to put dot, dot, dot. And then I want to show the very last calculation. So maybe someone can fill in what the very last calculation would be if I went and did that in order. Okay, there we go. So this is showing your work. It's basically saying here's how we would have calculated the chi-square statistic. But honestly, we're not really going to take the time to do that. So I'm just going to put equal, or maybe I could even put the equals right here. So my chi-square equals this. And so I'm going to go ahead and write the answer here as soon as I plug this into the calculator. And that's why I left the table here so that you guys could actually see what's going down. If I can erase, there it is. So I will let you plug those numbers into your two matrices. And now this is going to be a 2x3 matrix because we have 2 rows and 3 columns. And so you can edit your matrices. As soon as you get those edited, you can plug it into your chi-square test and come up with your chi-square statistic. It'll even tell you your degrees of freedom, which you should be able to figure out pretty quickly. All right, so we've got this. As far as the degrees of freedom go, it tells you right here you have 2 degrees of freedom. But again, just a reminder, to find your degrees of freedom, it's your number of columns, which we have 3 columns and 2 rows. So it's going to be 3 minus 1 times 2 minus 1. Number of rows minus 1 times number of columns minus 1, which gives us our answer of 2 degrees of freedom. So if you needed to do that for a test and ask for the degrees of freedom, you need to know how to find that on its own, but it's not a complicated thing to find. Okay, there we go. Now we can come to a conclusion about this. All right, and we can draw a conclusion. What would our conclusion be here? Let's just verbalize it. And I'll just get you started. Because the blank, so see if you guys can verbalize what our conclusion here will be. Uh-oh, I'm asking you guys to talk.
I just don't know.
Yeah, what would our conclusion here be?
It would be, so it would be statistically significant, so we reject the null hypothesis.
I'm just confused with the null hypothesis.
The null hypothesis is that there is no difference between.
Oh, right. So there is a difference.
Right, so there is a significant difference between the expected and the.
But I just meant in I was confused about context with that.
Okay, there we go. So that's a fair question. So yeah, just to verbalize it, if you want me to write it down, I'll do it. But because our p-value of 3.24 times 10 to the negative 6 is less than our significance level of 0.05, we reject the null hypothesis. There is convincing evidence that there has been a change in the use of statistics. And now our real alternate hypothesis is that there is a difference in these different samples. But now we can look at it further and we can say, what has the change been? And does it look like statistics is being used more often or less often? So we're moving through time that way. More stats. And we can also compare that to the expected counts. Like this was 269 essentially expected, and there was only 242. So that was less than expected. This we had 252 expected and 271. So, and this one was less than expected in 1978, 79, but more than expected in 2004, 2005. So it looks like stats is being used more and more through time. Okay. So that is our conclusion. I can clear all this. And that is the chi-square test of homogeneity. Chi-square test that we're going to do tomorrow is mathematically the same, so that's good. You're just going to kind of reinforce this idea. It's different conceptually, and so we need to know when to apply one versus the other. But besides that, if this is making sense today, tomorrow should be an easy day. So you have a couple of problems to look at in your homework tonight for practice. So if you have any questions on anything that we've done so far, feel free to stick around and ask those questions. If you are good to go, you can have a wonderful day, and I will see you tomorrow.